In part 2 of section 15, we're going to be working on writing a polynomial function. Now, when we start writing functions, that requires us to have an understanding of the domain as well as the equation that is necessary for whatever the function criteria is. So on example 15.3, we're told define a polynomial function. So every time we see define a function, whether it's a polynomial or a square root function or an absolute value function, whatever it is, you always have to have two parts. You have to have a domain, and you also have to have the appropriate equation. The equation helps you to actually create the mapping, and then the domain tells you what values to use for your mapping, because a function is just a type of mapping. So there's some conditions here. Condition number 1, we have to have a degree 4 polynomial. Now, since we have to have a degree 4 polynomial, the linear factorization theorem says that I would have to have something like a times x minus c1 times x minus c2 times x minus c3 times x minus c4. Degree 4, 4 factors, 4 zeros. It also says that we have to have zeros of -2 and 0. So -2 and 0 could be used to represent C1 and C2. So I'm going to come here and I'm going to say, let's let C1 be equal to -2, C2 could be equal to 0. And there's another stipulation. It says -2 is going to be a 0 of multiplicity 3. Now it's a good thing we have that statement, because I'm not going to be able to create a degree 4 polynomial with only 2 zeros. I have to have 4 zeros. I need a C3 and I need a C4. C3 and C4 can both be -2. So that way I have a total of 3 -2's, and then I have 0 giving me my total of 4. So looking back at the criteria here for our polynomial function, degree 4, check. -2 and 0, check. Multiplicity of 3, check. And there's no other restrictions, no other requirements here for our function. So if there's no other requirements, then I'm going to go ahead and select A to just be 1. 1 would be the nicest lead coefficient we could have. When we do factoring, this is the coefficient that we like to have at the very beginning. If there's no requirements that would say otherwise, I would just pick A to be 1. And then we're going to get the following statement. Well, actually, take that back. Let's do this next. We need to give a name to this. Let's go ahead and call this f. So that's going to be f of x. Now we'll substitute in f of x is going to be 1 times x minus -2 times x minus 0 times x minus -2 times another x minus -2. And cleaning that up like we did in example 15.2 A through D, we would drop that 1, let it be implied, giving us x plus 2 times x plus 2 times x plus 2. And anytime I have factors that are the same, I can always collect them together with an exponent, and I'll write this as x times x plus 2 cubed. This represents the factored form of our equation. Now, most of the time, when we're being asked to define a polynomial function like this, we typically write the answer in standard form, not in factored form. Factored form is just a way for us to eventually get to standard form. And we do this because the linear factorization theorem starts us off in factored form. So what I'll do next is go ahead and multiply this out to the point where we can see the individual factors. So in other words, I'm just going to go back to not having an exponent and I'm going to start thinking about how I would multiply all this stuff together. I'm going to take the x factor and multiply it by x plus 2, and then I'm going to take the x plus 2's at the end and I'm going to multiply those together. This is going to result in the following: x squared plus 2x times x squared plus 4x plus 4. And we are still technically in factored form. It's just not a linear factorization anymore. It's two quadratic factors. So we're kind of in a limbo stage here. I want to go ahead and take it further by multiplying x squared and 2x to the x squared plus 4x plus 4. That requires us to do 6 distributions, and you'll also need to combine like terms. I already have the result of that. It is going to be x to the 4 plus 6x cubed plus 12x squared plus 8x. And that would represent the standard form of our equation. Back at the top, we had discussed that to define a polynomial function, we need both a domain and an equation. I'm going to put a check mark next to the equation. That's done. Now, as far as the domain is concerned, the domain is going to be the largest possible domain. And when we're working with a polynomial, the largest possible domain will be all real numbers. So we'll start the function definition with the name of the function. That's going to be f colon. Then we write down the domain of all real numbers. And the domain, by definition, has to always map to other real numbers. And this is going to be given by the equation f of x equals x to the 4 plus 6x cubed plus 12x squared plus 8x. And we'll box that in as our final answer, as it is the polynomial function of degree 4 with zeros -2 and 0, where -2 has a multiplicity of 3.